Part 2 of the Fundamental Theorem of Calculus says that if f is continuous on a closed interval from a to b, that's lowercase f, then the definite integral from a to b of lowercase f of x dx is equal to uppercase f of b minus uppercase f of a, where that uppercase f is any antiderivative of the integrand lowercase f. Or in other words, uppercase f prime of x is equal to lowercase f. This is the thing that's going to make our work so much nicer in just a bit, but first we're going to prove it. By the Fundamental Theorem of Calculus Part 1, we had a function g that was defined as an integral, and we said that g prime of x is equal to f of x, which means that g is an antiderivative of lowercase f. If uppercase f is any other antiderivative of lowercase f, then g minus f is equal to c, a constant. That is, if I have any two antiderivatives of the same function, they differ at most by a constant. To see why this is true, we're going to do like a little proof within a proof. Let's define h of x to be g of x minus uppercase f of x. Then h prime of x is equal to that g prime of x minus f prime of x. But we've said that both of them are f of x, right? They're both antiderivatives. So the derivative of each one is f of x, which equals 0. So h prime of x, we've said, is equal to 0 for all x. What we want to say about that is that h is a constant. So we're going to find two numbers, x1 and x2, in the interval from a to b, and we'll say x1 is less than x2 without loss of generality. Since we've said that h prime is equal to 0, we know that h is differentiable, in particular on the interval from a to b, and continuous on the closed interval. That was an open interval a second ago. Continuous on the closed interval from a to b, because differentiable implies continuous. By the mean value theorem, there exists a c in the interval from x1 to x2 such that h of x2 minus h of x1 is equal to h prime of x times x2 minus x1, but h prime of x is equal to 0, we already said. So then h of x2 minus h of x1 is equal to that 0, which means that h of x2 is equal to h of x1 for all x1 and x2, which means that h is a constant. Okay, so that proves the proof within a proof. We're at this point now. If g minus f is equal to a constant, then we can say that f of x, I meant to say g of x, is equal to f of x plus c. And so g of b is equal to f of b plus c, and g of a is equal to f of a plus c. G of b minus g of a is then equal to f of b plus c minus the quantity of f, it's all uppercase here, f of a plus c. The c's subtract out, brackets there, and so g of b minus g of a is equal to f of b minus f of a. But from the Fundamental Theorem of Calculus Part 1, g of b minus g of a is the integral from a to b of f of t dt minus the integral from from a to a of f of t dt. These are lowercase f's, of course. And an integral that goes from a to a is going to evaluate to 0 because delta x would be a minus a over n, right? And that's going to equal 0. So flipping things around and making a substitution here, the integral from a to b of f of t dt, lowercase f, is equal to uppercase f of b minus uppercase f of a. Here's the, that finishes the proof. Here's the punchline. If I want to compute the value of a definite integral, I find an antiderivative and evaluate it at the upper limit, evaluate it at the lower limit, subtract the two, and that number is the answer. I don't have to go through that limit process anymore. Woohoo! At this point, I should point out that we used the Fundamental Theorem of Calculus Part 1 in the proof of the Fundamental Theorem of Calculus Part 2. This Part 1 and Part 2, they are not universal. It's the author that I'm pulling this from chose this part of it to be Part 2 and the other one to be Part 1. With some authors or some writers, they've chosen this one to be the Fundamental Theorem of Calculus Part 1, and then what we called Part 1, they call the Fundamental Theorem of Calculus Part 2. The proofs then become completely different, but one thing that is similar about them is the proof of what we did as the second one, it's completely different, so then they prove that. And then we go to what we call the first one, what they might call the second one, and they will point to, hey, based on what we just did, and then they will give a whole different proof. So I just want you to be aware, the Fundamental Theorem of Calculus, like the parts, Part 1 and 2, it's not a universal thing. The two parts together are a universal thing.